All right, so yesterday we started talking about the idea of uncertainty, and we said that all of our measurements come with some degree of uncertainty. And because of that, there's a couple different ways that we analyze it, right? First, we talked about the uncertainty comes from two ways. It can come from random errors or systematic errors, right? Systematic errors are basically things that are wrong with our measuring device. And so when we look at how they affect our data, they basically affect our data the same way all the time. So we're getting an answer that is skewed from what we're supposed to be getting, quote unquote, right? But all of our measurements are very generally precise. They're all within the a very same range, right? Whereas random errors result from a couple different things, but the biggest thing is basically just we have uncertainty in the measuring tools that we use. Not that they're wrong, but there's just uncertainty that we use as far as how we read them and the markings that they have and stuff like that. So then we started talking about how do we take into account this uncertainty when we're using these measurements to try and come up with some kind of a correlation or some kind of an answer to whatever it is that we're trying to question. You have this, and we did it yesterday. Can't. This is a review, okay? So, we talked about, where are we here? Okay, so first let's go back here. First we talked about absolute uncertainty. Oh, no. First thing we talked about was absolute uncertainty, where basically we're just looking at a range of the measurements that we got. And we did this example in class, right, where a student got a set of measurements, right, and we kind of looked at this one that was 2.8, and we thought that it was a little bit out of the range for a random error, and so, but it's not a systematic error because all the other values are very close to one another, so we just kind of get rid of that one. We took an average of the remaining 6 to find the average value, and then just looked at the range over which our other measurements occurred to figure out the absolute uncertainty in this measurement that we took. Okay? Then we talked about fractional uncertainty, where we're looking now at like proportions or percentages of our actual measurement, right? In a fractional uncertainty, we take the range of our measurement divided by the measurement itself, and that gives us, like I said, basically a decimal, right? You know, what portion or what proportion of our measurement is the uncertainty range, right? And so here we looked at these 6 measurements. First thing we did was take an average. We rounded it to 5.6 because of the significant digits, right? There's 2 significant digits in all those numbers, so we rounded 5.6. Then we just looked at the range of our measurements, the lowest measurement being 5.4, the biggest measurement being 5.8, right? And that gave us our range of plus or minus 0.2. But then for fractional uncertainty, we took the range, divided it by the value, and that gave us a fractional uncertainty of 0.036. You turn that into a percentage by multiplying by 100. Okay? So that's just of a set of numbers, right? But then when we start looking at mathematical calculations, we have to look at the uncertainty of the values that we are calculating with. When we're adding and subtracting, we just add up the uncertainties, right? So here, right, for this, the sum of the lengths, we just added those 2 values together, but then we have to find the uncertainty of this sum value, we have to add the uncertainties of both of our original measurements to get that there, right? Same thing is true of the difference. We just take the difference of these 2 numbers, right? But then to get the uncertainty range, we have to add the uncertainties together, okay? Then percentage uncertainties, we're looking at the uncertainty range over the actual value, turning that into a percentage.
That's kind of nice that like both like addition and subtraction is the same method to add together, and multiplication and division is the
Same
same.
thing, yeah.
It's just kind of nice.
Because, I mean, addition and subtraction are basically the same mathematical operation, just going in opposite directions.
Yes.
Same thing with multiplication and division, right? It's, you know, repeated addition or repeated subtraction. Yeah. And then when we talked about multiplication and division, right, we take the sum of the uncertainties for each individual operation, right? We have to add those together to get the range of uncertainty. And at the end, we did this calculation where we looked at the area of the rectangle. Okay? Good there? Okay. Today, let's start here with graphical representations, right? We graph something because it's easier to see the relationship between the numbers, the trends in the numbers, a lot of times visually than it is just looking at a list of measurements that we took. So when we're looking at the graph, it obviously gives us the trend in the measurements, right? This is a linear relationship. This is a power relationship. It's like it's actually a square root relationship. That's how that works. So we're looking at the trends in those numbers, but we represent uncertainty on our graphs with our error bars. And so we're saying that the actual value of this measurement could be anywhere within that range that is a square or a rectangle, depending on what your error bars are like, around the measurement that we took, right? And this range that the error bars encompass, either horizontally or vertically, come from our absolute uncertainty of each individual measurement, right? When we're taking our random errors into account, the range that we measure, et cetera, et cetera, et cetera. We should find that when we draw our line of best fit, which is meant to represent the relationship between those two variables, that our line of best fit should fall into the range of all of those measurements as outlined by the error bars, right? Because if we're not, then we're obviously doing something wrong, right? So that's like down here, if we have these, well, this isn't actually good, right? Here, this best fit line only falls into the range of the error bars of 2 of these 5 measurements, but this one that's like really, really off, that's where we would sort of assume, okay, maybe there must be something wrong with that measurement and stuff like that, okay? When we then factor in the uncertainty into making our graph, we have to then show how that uncertainty affects the values that we can interpret or extrapolate from that graph, mainly slopes and intercepts, because a lot of times that's what we're looking for, right? So, error bars, blah, blah, blah. One thing I talk about in this graph of the error bars, you can see that for each individual measurement, they don't necessarily have the same error bars, which I suppose they talk about that it is a possibility that that could happen. But when I look at it, we said that this range is really a result of the measurement tool that you're using, right? The individual marks in the measurement tool and stuff like that. So I don't see how you could have error bars that are different lengths unless you were using different measuring tools each time. Like if you used a different ruler to measure this dot versus this dot. I would say in most cases you should have the same error bars. And the next part of this discussion talks about the idea that if you have a situation where you have error bars that differ from data point to data point, don't mess around with it. Like, use the worst value and assume that all of them are the same, basically. So use your biggest range of uncertainty and just assume that's going to be the uncertainty for all of your measurements, just to make it easier. Technically, there could be different error bars for different quantities or for different individual measurements, but just assume they're all the same, because that makes, if you use the biggest range of uncertainty, that should fit all of your other uncertainties in there. Okay. Good? All right. When we talk about the uncertainty of the slope, basically what we do is we draw in the slope that could have the steepest gradient, right? The steepest slope, versus the one that has the shallowest gradient, the shallowest slope. So we take the high end of the uncertainty here and the low end of the uncertainty here, and just draw that straight line. And then for the shallowest slope, we take the low end of the uncertainty here and the high end of the uncertainty here, and draw that line. So technically what we're saying is our slope should fall somewhere along in between these two lines, okay? Because that's what the uncertainty gives us. And then as far as the intercept, right, if you've drawn the steepest slope and you've drawn the shallowest slope, that's the range of that's the uncertainty range for your intercept. It has to be one between one of those two things. Okay? Good there? Yep. So the packet I gave you yesterday, it had the sample problems. I don't like the way that this problem was stated, but I didn't write it, so. So it says, use the following graph to state the gradient and the y-intercept with uncertainties, okay? All right, so it just has a graph, and then it has 3 lines, right? The line in the middle with the blue dots, that's your measured value, so that would be like your absolute values, you know? The red boxes would be your steepest slope. The green triangles would be your shallowest slope, right? And like we did, they just went to the top of this error bar range to the bottom of this error bar range, drew a straight line. Bottom of this error bar, top of this error bar, straight line, okay? So this value, right, that's going to be your value, right? That's going to be like what we assume to be our absolute value, or our not absolute value, like it's the best value if you want to say it that way, right? The one thing they want us to do on this is to make sure that we take into account significant digits, right? Values for distance have 2 significant figures. The values for time have 2 significant figures. So if this is a distance versus time graph, what is the slope of this graph telling us? Speed, right? Because slope is rise over run, distance over time, that's a speed, right? So here, for the gradient of that graph, gradient's fancy name for slope, right? We go to this one here. This number has 4 significant digits as it's written. We can't have 4 significant digits, right? So the gradient for that graph is going to be 0.30, right? That beginning 0 isn't significant, okay? And then, as far as a range goes, 0.34 for the steepest slope, 0.26 for the shallowest slope. That's going to lead us to what as far as our range goes. Plus or minus 0.4, right? 0.04, you're right. Okay. Does that make sense? You okay with that, Clark? Point 0.3 is the middle, right? The steepest slope is 0.34. The shallowest slope is 0.26. So that's just, you know, a range of 0.04 up or down. Does that make sense? Yeah. And then, as far as the y-intercept goes, right? Again, this is our accepted or our best value, whatever. 2 sig digs would take us to 1.3, right? And then 1.1 on the top, or on the bottom end, 1.5 on the top end, right? So we'd go plus or minus 0.2, right? But then we probably should have another, no, not that one. Because now we're consistent with the range on our measurement. Our uncertainty is consistent with the range on the measurement. Does that make sense? That's literally what they want you to do there. Okay. Woo. And then, from a unit standpoint, your gradients, your slopes, and your intercepts do have units, because we put them on this graph and they're representing real world values, right? So we said the slope on this graph, because it's a distance over time graph, that's going to be a meters per second number, right? And then the y-intercept, because it's just a single value on the y-axis, and the y-axis is a distance value, that would just be meters. Good there? Okay. If you want, on that same page, there's another problem. Here's the answers to that problem if you want to like go back and look, if you want to write down the answers and then go back and verify them. So. Good there? All right, so let's start here. As promised, I copied for you a sample paper 3. Okay. And so, just for the sake of, this is going to mess me up here. Okay. So here's the beginning of sample 3, okay, or paper 3. Like it says on the front, okay, there's 2 sections to paper 3. Section A, answer all questions. That's going to be your uncertainty questions, okay? Section B, answer all of the questions from one of the options. So you see here that all 4 options are going to be there. You only have to answer the questions for one of the 4 options. So don't get the test and look at it and go, holy crap, because if you look here, it's like here, this test, this one starts on page 60, right? Okay, and the answer key starts on page 100. Okay, it's 40 pages. You don't have to do 40 pages. You only have to do about 8 of those 40 pages, right? So make sure when you get there, you're doing the, you're only doing the things you need to do. Okay. All right, good there. Okay. All right. Well, let's take a look here, and let's go. All right, so let's take a look at section A. It says answer all the questions or your answers in the boxes provided. So this test, just as a general note, there are some tests that you will write directly on the test. There are some tests that you will write in like an answer book, okay? Physics is one of the things that you write directly on the test, and then we send that test back. With the answer books, there'll be like a separate question book, and then the answer book that you write in. History, lit, math. Is math a separate? I can't remember if math is it's some of both. Okay, so yeah, so some of them you're writing directly on the test, some of them you're not. We'll take care of that as we go along. And I think unless I'm mistaken, physics is the only one that you have a multiple choice section on. So I believe that's the only one that you have a multiple choice section. So. Okay. So it says here, the speed of sound in air, v, was measured at temperatures near 0 degrees Celsius. The graph shows the data in the line of best fit. The error bars for temperature are too small to be drawn. Okay? So, a student suggests that the speed of sound, v, is related to the temperature, theta, in degrees Celsius by the equation, v is equal to a plus b theta. Okay? So, where a and b are constants. Okay? First, just hopefully this is, you look at this and you're like a duh, okay, but just to make sure, right? What kind of relationship are we talking about here? It's a direct or some linear, we call it a linear relationship, right? And as a direct or linear relationship, it should have the equation of a straight line. You guys always learn the equation of a straight line is y equals mx plus b, right? This is y equals mx plus b, just in a different order, right? V is on the y-axis, theta is on the x-axis. That means that b is going to be what? It's going to be the slope, right? And that means a is going to be your what? The y-intercept.
Yeah, it's going to be.
Oh, is it? So if we go with what we do it for, that means b is what is
x? B is m.
B is m and a is b, right? So, but if we talk about them in general terms, right? Yeah.
I'm sorry.
Okay.
I
You said b was a, and I was like, I'm just
sorry.
gonna slide past this, but okay, yeah, okay, yeah. Right. All right, so it says, determine the value of the constant a correct to two significant figures. Okay, we said that a represents what about this graph? Y-intercept, right? It's pretty easy. Go up here, right? So there's 320. That means that each horizontal line is 1 degree Celsius, right? No, sorry, 1 meter per second, right? We're somewhere, you know, right? Probably between 329 and 330. Yes? Did I do that right? Yeah. No? But you can't write 329 because that's 3 significant figures, right? So I rounded mine to what? 330.
330 plus or minus.
No, the value. Doesn't say the range, right?
Oh.
It says the value, okay? So in that case, right, 330, it should have a unit, right, because it's a real world measurement. What's going to be the unit on A? Meters per second, because that's what axis it's on. All right, good there? All right, next for part 2, it says estimate the absolute uncertainty in B. Okay, so here B we said represents what about this graph?
Or we know the slope.
The slope. Okay, so
You know what I mean?
here's what we have to do. By the way, you're allowed to have straight edges and stuff on the test. So.
Oh, cool.
What?
Oh, yeah. I want the circle one.
I don't. Was it angle
That's an old
thermometer?
planer rule.
The angle thermometer.
What?
Let's see if this works. Two lines, Fuad, 2 lines, right? So if we are talking about the absolute uncertainty in B, we're looking at the slope, and so we have to draw in the line with the steepest possible slope and the line with the shallowest possible slope, okay? So, using my fancy tools, I am going to draw a line that starts, so I'm going to start it here and draw it to here, right? That's the steepest possible slope that that line could have based on the uncertainty. And then I'm going to start the other one here, maybe, and put it there. Okay? Because these are slopes, we have to calculate the slope of each line individually. Okay? So, we just go rise over run, right? So, for red, I said it started at 344. And it ended at 314. Does that make sense? So if I'm calculating the slope of red, technically, sorry. Final minus initial. Yes. Okay. And then the run is along the x-axis. It started at 20 degrees Celsius. It ended at negative 20 degrees Celsius. So that's a change of 40 degrees on the x-axis, yes? All right. So this one is actually a pretty easy one to calculate. That's the slope of that line, yes? Okay. Then for blue, right? Technically that'd be a negative slope, but whatever. So then, right? 318 minus 340. That also takes place over 40 degrees Celsius on the x-axis. Say again? That's okay. No. Keep what you have. Because it's your interpretation, right? You know, so as long as you're going through the process, yes, that's the important part. And then, right, if we want the absolute uncertainty, we need a value to build the uncertainty off of, right? So the last thing we have to do is find the slope of this line, right? The one that they drew for us, right? And that's the purple. Okay. Yes.
Yes.
And then I got that as 0.625. So first, how many sig digs are we talking here? It told us to do 2 in the first one, so we should keep 2, right? So for our value, 0.63 plus or minus, how far away are we here? 0.12. But here we're only So which one should we use? The bigger one, right? So use the bigger range. Okay. Say again? She's got it. Don't worry. And then remember, this is a graphical representation of real-world data, so it should have units on it, right? What's the unit on the y-axis? Meters per second. Say again? No, that's velocity in meters per second. Yeah, that's kind of confusing. I wouldn't label my graphs that way, but that's how they choose to do it. So, right. So meters per second, but then per degree, right? How's that? To understand where we did, what we did. All right. Student calculates that B is equal to 0.593 meters per second then minus, or whatever, okay? State, using your answer to A2, the value of B to the correct number of significant figures. So, how many significant figures does this calculation need? 2, right? So that we would round this then to what? Here, this 0 isn't, the first 0 isn't significant. That means 5 is and 9 is. And then the value right after the 9 is 3, so we don't round that up, right? So that's going to be 0.59 for 2 significant digits. 0.60 would be 2 significant digits, but that's not how that number would get rounded. That is 2 significant digits, but it's not how that one would get rounded. All right. Part B says, or part BI, estimate the temperature at which the speed of sound is 0. So, how are we going to do this? Say again? Problem with that is what? Well, not so much that. On the y-axis, what's the lowest value that you have there? 310. What is this question asking you about? 0, right? But underneath the original graph, it did give you a what? And it gave you an equation, right? And so we figured out what that equation was, right? We know the slope of that equation, okay? Yeah. Right. Is everyone following me? What, are you following me? You can say no, it's okay. Yeah. Don't even worry about that right now. So.
It's 0.63 was for I2, just to be clear, right?
No. It should, though, Graham, with this, even though we didn't calculate it that way, because this slope is sloping this way, that should be a negative value, right? So that when you plug the numbers in, you actually get what? Oh, you're right. My bad. So.
How'd you get 330?
What's the very first question that the thing asked you for?
It asked, determine the value of constant A.
And we said constant A is what in this graph?
Is the y-intercept, and that would be 330.
There you go. Oh no, my bad. The slope is not negative, it's positive, right?
What?
Yeah. This is a positive slope, yes. My bad. That's why. Duh. Technically, when we were calculating all of these slopes, this 40 is negative because it's final negative 20 minus initial, which is positive 20. Sorry, everybody. So that slope should be positive, and then Graham, when you do that calculation, right, what do we end up with? -523. Yeah. So, right? One thing we should fix on this, right? How many significant digits should that? We should have 2, right? So, okay. Austin, do you understand where that came from?
I don't know how you got the,
How you got what? You don't know how we got what?
oh, it's 0 because my one.
Yeah, that's what we did, because it was asking you for when the speed of sound would be 0, so we plugged in 0 into this value here, solved for theta.
So it's -2 divided by 0.63, which comes out to be negative.
All right, good there?
And
So,
wait, 20, is it 20? It says 24.
yeah, how many significant digits?
Um,
So then just to wrap this one up, for B2, or BII, it says explain with reference to your answer why the student's suggestion is not valid. All right? Say again? Well, you know that, but then why is, so what are we assuming in this case here? We make some assumptions with this graph. Say again? No. What do we assume about this? So, are we good about how sound travels through air, right? As a longitudinal wave, right? What do we assume about all those collisions of those air particles? They're perfect collisions, right? But as we get slower and slower and slower, right? What do we know about those collisions? They're not. Yeah, they're not going. Yeah, they're not going to be perfect anymore, right? The other thing is, because we're talking about something traveling through air, one assumption we make about air molecules, that gets back to the perfect. That gets back to the perfect collision thing. We also assume that air molecules actually don't have any volume,
oh, yeah.
because when you compare the volume of the individual molecules to the volume of the gas as a whole, they're insignificant. But when we slow them down, now they become significant because they get closer together, right? Also, and these are all possibilities you can throw in there, right?
I also think they don't touch.
Yeah, well,
They don't fly.
when they,
have the line.
no, when they collide, see, that's one of the things we assume, is that they collide even though they don't have any volume. That's, the other thing is, we're doing this in a gas, but what happens to that gas as it gets colder? Eventually, what does it turn into? Well, first it has to turn into a liquid first, right? But yeah, it doesn't stay a gas the entire time until it gets down to the slowest speed. That's a hard one to do. To get. That's when we start getting into. Say again. It wouldn't be a linear. It wouldn't be a linear relationship anymore. We make no, the data was fine, but we're making assumptions about extrapolations with that data that are right. We're assuming basically that all the conditions remain the same as far as that the measurements were taken, and that doesn't happen because of the change of phase and all that kind of stuff. So, all right, tomorrow we'll talk about some more uncertainties on finish up that part 3. And then we'll get ready for Thursday when we start looking at motion stuff. I got some stuff for you guys to work on over break, which I'm sure you'll be happy about. So.